皆さん、ブースは楽しんでいただけましたでしょうか。全部見られなかったという方は、後半の部の終了後、17時からブースのセッションも行いますので、その時ぜひご覧になってください。さて、ここからは高校生の皆さんによる研究プレゼンテーションです。今回は宮城県より仙台第一高等学校、仙台第三高等学校、古川黎明高等学校の3校と、アメリカメリーランド州よりエレノア・ルーズベルト高校の皆さんが、それぞれの研究成果について発表してくれます。彼らは皆英語で発表を行います。そしてそれぞれの発表後、前半に講演してくださった5名の研究者から英語で質問をしてもらいたいと思っております。それぞれとても面白い研究を行っています。ここから同時通訳はありません。皆さん、彼らがどんな研究をして、そしてどのような研究者とやり取りをするのか、皆さんも頑張って理解してみてください。私もここからは徐々に英語で司会をしていきたいと思いますが、発表前にタイトルと概要だけ日本語で説明いたします。We'll have a 6 presentation in this session. Each speaker from Japanese high school have 12 minutes for the presentation and 3 minutes for the discussion. 3 speakers come from Eleanor Roosevelt High School. They have 5 minutes presentation and 1 minute discussion. The first presentation is about the research entitled A Method to Change the Color of Metal by Oxidation by Sendai Daisan High School. 日本語の講演は、日本語のタイトルは、酸化によって金属の色を変化させる方法です。彼らは金属に熱を加えたり、溶解中で電気を流したりして酸化をさせることで見事な色の変化を実現しています。発表の最後、彼らから素晴らしい提案がありますので、該当する方はぜひ挙手してください。ではよろしくお願いします。
Good afternoon, everyone. My name is Shotaro Yuzawa.
My name is Masahito Yamazaki.
My name is Yusuke Sato.
Today, we would like to tell you about our study. First, what color do you imagine when you think of metals? For example, iron, alumina, and nickel. Look at this picture. Most of metals are silver color. Other metals have gold color and copper color. Then, what metal is this yellow metal? What do you think? In fact, this is nickel. By the slide of a while ago, nickel is a silver, but this nickel is yellow. This is the point of our study.
We want to tell you about this main message. We could change the metal into so many beautiful colors. And our coloring method has a lot of good points. So it is suitable for coloring the part of many delicate machines. And this method can reduce human errors. Next, purpose of our study. First, to change metal's color freely. Next, to understand the principle of coloring, changing.
This is the flow of our study. First, selecting metals. Next, anodizing. Finally, heating. First of all, we must find the right metal in our experiment. We heated 6 kinds of metals in a gas burner. Look at this movie. Color is changing. Result. As you can see, we can see the change of color of nickel, copper, and iron. But the iron is likely to rust. Therefore, we decide to use nickel and copper. Next, oxidation method. There are 2 kinds of oxidation method: anodizing and heating. Anodic oxidation is one kind of electrolysis. If you electrolyze the water, the oxygen is generated from positive side. We use this oxygen. This is our anodic oxidation device. This is a figure. Solution is H3PO4. Positive side is nickel. There are 2 kinds of anodic oxidation experiments. First, the control experiment that changes voltage and time, and the control experiment that changes concentration and time. Result. Look at left figure. All the metals change their color to light yellow. Therefore, we could not see the differences by voltage and the time. Next, look at right figure. All the metals change their color to light yellow too. But look at this line. The longer the time is, the clearer the yellow becomes.
Next, heating experiment of metals. First, we heated the metal plate using muffle furnace and crucible. In other words, and next, observe their colors. In other words, and we heat metal plate using oven and ceramic cup. Next, flow of this experiment. First, set metal. Next, set temperature. Finally, set heating time, and we got many different colors. Next, result of heating experiment of nickel. And color change, light yellow to yellow, to orange to purple, to blue to light blue, to gray and black, from 500 degrees to 800 degrees. And we got, as you are probably aware, even if we change metal's heating time, the colors appear in the same order. Only heating, we got many colorful metal plates. Next discussion. We could see a little regularity from this result. It is that change from low temperature to high temperature is similar to change from short time to long time, as Rose showed. Then, we thought what causes change of metal's color as we heat them longer at the same time. Then we thought what causes change of metal color, and we thought it is oxide film. In other words, as the slide shows, we thought oxide film thickness controls metal's color. Our result is likely to be caused by the principle.
Next, we conducted the heating experiment of copper. The way to do this experiment is similar to that of nickel, but the lowest temperature is 170 degrees and the highest is 230 degrees. From low temperature and short time, the result is orange to purple to silver to gold to light yellow to the color like original copper. Discussion. According to the research, there is copper oxide in coppers heated by 170, 180, 190 temperature. So it is thought that copper oxide has influence on these color changes. And in over 200 temperature, there is not only copper oxide, but also copper 2 oxide. So it is thought that these two cause these color changes. Our result is likely to be caused by these two principles. Summary. First, we could change only certain kinds of metals to many beautiful colors. Second, we could consistently change these metals to colors we expected by controlling temperature and heating time. Third, changing just one condition didn't change color. By the way, please look at these three pictures. From our experiment, we could change copper to silver or gold color like this. Therefore, if we improve our experiments, we may be able to change bronze medal to silver or gold medal. So, if there are any person having a bronze medal like this, why don't you entrust it to us? We will give you back beautiful gold medals. Thank you for listening.
Oh, thank you very much. Professor Hirose, do you have any question or comment?
First of all, thank you very much for a very nice presentation. I enjoyed a lot. Thank you very much. I have one question. Okay, so if you have more opportunity to conduct more experiments, okay, what do you want to do? What type of experiments do you want to do?
Thank you for your question. We are planning to use other acids, the experiment of oxidation, and also we are going to consider the measurements of metal thickness. We would like to do much more experiments and observe the rules about changing colors.
I agree. It supports your conclusions. Thank you.
Thank you. So, Dr. Takayama, could you ask some question or comment?
I'm interested in your research. So I have one question of color of Nikkei. So please show the slide. Okay? No? So please,
Nickel. Which one? please?
all data side by side.
一個ずつ全部
全部。
一個ずつ全部見たいって言ってますので、ちょっと最初からざーっと流して。
That's okay.
This
So,
is okay?
Yeah, this is okay. So, when you heat at 5 to 5 degrees C and for 30 minutes, that color is purple, look like not yellow. So, the result is intrinsic or anything error. So, please tell me.
これの一番下の左から2つ目、はい、これがなんか合ってないんじゃないって言ってるんで。
Thank you for your question. We think it is human error. Sorry. We would like to do same conditioned the experiment more and get right date.
Yeah, that will be very, very important for scientists.
Okay, thank you.
So thank you very much. Thank you very much, and ask again. So I would like to introduce a second speaker, a student from Sendai Daiichi High School. The title of their presentation is very difficult. Potassium permanganate sodium neosite redox titration, the effect of manganese ion catalyst. So please start. すいません、ちょっと日本語で、日本語のタイトルは、過酸化マンガン、硝酸ナトリウム酸化還元適定、マンガンイオンの触媒としての効果です。誰もが教科書で一度は見たことがある、レドックスタイタレーション、酸化還元適定、そんなフロックから知られている反応で、彼らは大きな発見をいたしました。これは教科書にどこにも書いていない素晴らしい発見であり、2013年の現在も研究が進められている現象であります。どうやって発見に至ったか、そこから彼らはどんな実験を行ったのか、じっくりお聞きください。Go, please start.
Hello everyone, my name is Kenichiro Munakata, and this is Tomohiro Seno, and this is Takumi Matsunaka. We'd like to start our presentation.
Our school, Sendai First High School, has over 120 years of tradition. Its cheering style has been one of its traditional characteristics. There are 12 members of the chemistry club of our high school, and among them, 7 members have been concerned with today's presentation and experiment. We examined whether manganese ion works as a catalyst or not in potassium permanganate and sodium oxalate redox reaction, and whether other ions can have the same effect as manganese ion or not. I want you to look at these two animations and compare the velocity of two titrations. Look at the left side.
Now the purple color in the left beaker disappeared. In spite of the same redox reaction of potassium permanganate and sodium oxalate, the velocity is considerably different. This is the very point we are interested in and focus on. In fact, one is the conventional way of this reaction, while the other shows our original idea, and in this method of new reaction, the velocity is much higher than that of the conventional way of this reaction. Look at the right side. Now the purple color in the right beaker disappeared. In order to calculate the velocity of this reaction, we measured the time for the purple colors disappearing about 1 drop of potassium permanganate. At the same time, we measured the volume of 1 drop many times and calculate the average volume of 1 drop. From the change in potassium permanganate concentration and the time, we calculated the velocity of this reaction. In the first place, what is titration in general? The purpose of this method is the decision of the unknown concentration. Let's think about the reaction of solution A and solution B. Solution A's concentration is known, while solution B's concentration is unknown, but its volume is known before experiment. When the proper volume of solution A is added into solution B, the indicator shows the finishing point by changing the color, so that we measure the added volume which is well balanced with solution A. From the known concentration of solution A and the volume experimental data of V and the known volume of solution B, we can calculate the unknown concentration of solution B.
So, what is oxidation, reduction, or redox titration? The term redox is short and convenient, isn't it? Although ordinary dictionaries don't have this term. This reaction involves oxidant giving electrons and reductant receiving electrons. When both electron numbers become the same, we can know the finishing time by the indicator, and we can stop the titration and calculate the unknown concentration. The redox reaction of potassium permanganate and sodium oxalate is currently explained that this should be undertaken at around 60 degrees Celsius and under the condition of shielding the light because of decomposition of potassium permanganate and at the same time speeding up the reaction. We can often see these instructions about this reaction in the high school chemistry textbooks, and even university entrance examinations in Japan. Such difficulty of this reaction caused us to try to find a new method of this reaction with our original idea. First of all, there is interesting and unusual characteristics about this reaction. The lower sodium oxalate solution concentration becomes, the higher of the velocity of the reaction becomes. From this strange tendency, we inferred that manganese ion generated continuously from the oxidant potassium permanganate through this reaction works as a catalyst. Based on this hypothesis, we conceived the idea of adding manganese sulfate solution as manganese ion to sodium oxalate solution in advance. And we expected that the reaction can be accelerated owing to added manganese ion. The reason for choosing manganese sulfate is that sulfate ion has no effect about this reaction. This is convenient when we focus on potassium permanganate and sodium oxalate reaction.
This chart indicates that when we add manganese sulfate solution to sodium oxalate solution in advance, the time for disappearance of purple color is shorter compared with the reaction without manganese sulfate solution, particularly in the beginning titration. This graph shows the velocity of this reaction, comparing the reaction with manganese sulfate solution as a catalyst and that with water as a control. We calculated the velocity based on average decrease in concentration of potassium permanganate solution per second. From this result, we can confirm that manganese ion surely works as a catalyst. In the next stage, we examine whether other ions have same effect as manganese ion or not. We added aluminum sulfate, manganese sulfates, zinc sulfates, magnesium sulfates, and water separately to sodium oxalate solution. And this graph is for manganese ion, and these graphs are for other ions. This chart displays that manganese ion worked effectively as a catalyst, while other ions have little effect as a catalyst. Here, we can ensure the important role of manganese ion. In summary first, during redox titration of potassium permanganate and sodium oxalate, manganese ion surely works as a catalyst. Second, other ions have much less effect as a catalyst than manganese ion. So, adding of manganese sulfate solution to sodium oxalate solution in advance is so effective in terms of heightening the velocity, which leads to saving time, energy, and conducting this experiment without a special bullet. using this new method of redox titration, we are trying to measure the mass of reducing sugar generated through hydrolysis of cellulose with appropriate catalysts. Thank you for listening.
Thank you very much. Dr. Hirose, do you have any question or comment? Dr. Itami, I'm sorry.
First of all, congratulations on your discovery of manganese catalysis in this reaction. I'm so surprised that high school student can also make such a discovery in very important redox reactions. So first of all, congratulations.
Thank you very much.
So from here, it's like more like a university, but what do you think about the mode of action, mechanism of this manganese catalyst?
So please look at this slide, and we are considering the mechanism of this reaction with or without manganese iron. Simply, permanganate iron and oxalate iron are both of negative ions, so that they are impulsing each other. So they are repulsing each other. Consequently, the velocity of the reaction is forced to be very slow. All reactions require the encountering of substances. Therefore, there should be positive ions connecting those negative ions. So we presume that these positive ions are supposed to be manganese ions. It is true that there are other positive ions, such as potassium ions and hydrogen ions, but these ions have effect of catalyst. In addition, from our experiments, other positive ions have less effect as a catalyst. So we considering these things, we think that the manganese ions as impurity or added ion make intermediate compounds with those negative ions. And then manganese ions back to the original. So manganese ion can be said out-catalyst in our opinion.
That's a beautiful assumption. Thank you very much.
Oh, thank you very much.
Yeah. By the way, I think you have a very good name, Kenichiro. Same
Thank you very
mine.
much.
Okay. Professor Guria, could you make some comment or maybe questions?
I would first comment in congratulations on your very clear presentation. I feel that I would be able to repeat your experiments, and that's always the first rule of scientific reporting, that the work should be reproducible and other people could do the same for themselves. So congratulations on a very clear presentation.
Thank you very much.
What is the next step? You are working with an immediate experimental plan, but other ideas on catalysis? What would you like to do?
職場について次何の実験とかやりたいですか？
So we are trying now. So we are now trying the experiment of measure the mass of reducing sugars as beta glucose and so on. Because of this redox titration, is able to measure the mass of reducing sugar, but because of reducing sugar has an ability of working as a reductant. So we are trying to this experiment, and we can do more experiment of this, and we want to make the result of this experiment.
Thank you. That's very clear, and good luck with that work.
Thank you very much.
So I hope you are enjoying your experiments. Yeah? Thank you again for the presentation. So we would like to move on to the third presentation. So I would like to introduce the third speaker, student from Fukuoka Reimei High School. The title of their presentation is Verification of Breed Difference Through Answer Culture. 日本語でのタイトルは、稲の薬培養におけるカルス形成率、細分化率、倍化率の品質格差の検証です。日本人の主食であるお米、その品質改良では、薬培養と呼ばれている花粉ができる薬のみを使って稲を育てる方法が取られています。彼らは品質ごとの薬培養の成功率の違いを検証しています。日本人の根幹をなす研究と言ってもよいでしょう。So go ahead, please.
Before the presentation, I would like you to ask one easy question. What did you eat this morning? Who ate bread this morning? Please raise your hand. All right. Who ate maybe donuts this morning? Then who didn't eat breakfast this morning? Fair enough. Then maybe most of you have eaten this, rice. Was it correct? Then one more question. Do you know how long does it take to make a new variety of rice? More than 10 years. It has a very difficult and long process to make your breakfast. But there is another way to make new varieties of rice more easier. And our presentation is about it. We will speak to you about answer culture. Reimei High School is in Osaki City, which is in an area famous for its agriculture. The former agricultural research station was next to my school. Now, the new school building has been built there. When I studied about the agricultural research station, I discovered it had created famous varieties of rice, such as Sasanishiki and Hitomebore. Oh, this is Sasanishiki. Also, I discovered some of the rice varieties are made by using answer culture. And that's why we became interested in answer culture.
We'll explain about answer culture. Answer culture is a process of making a clone using answer. The first step is to make a cross. A cross is a cell made from the answer. So this is called answer culture. The second step is despecialization. Despecialization is a step to make a plant which can grow successfully. The third step is doubling. Doubling is a process to raise a plant which can produce rice seed. The advantage is that we can produce new plant with completely the same trait. So we can produce new varieties in the short term. It has 3 problems. First, we can only small amount of crosses can get. Second, the amount of plant material made from the crosses is small. Third, some variety may not produce seed. The formation rate of crosses and despecialization rate and doubling rate are different with each variety.
Next, we will tell you about the difference between general pollination and answer culture. In the case of general pollination, basically the children F1 clues are given the half chromosome from paternal parents and maternal parents. Then F1 strains are mixed. In the case of F2, each strain also become half. Then good strains such as good taste and resistance to cold weather can't be established. In the case of answer culture, because of meiosis, the amount of the parent chromosome is half. We multiply the chromosome amount by using colchicine. Then we can produce a clone so good strains established.
Now we focused on the fourth problem. The formation rate of the cows, respecialization rate, and doubling rate are different with each variety. And we thought if we studied about it, it could help the agricultural research station. So we studied about variety, study which variety caused such a difference in rate. Our purpose is to examine the formation rate, respecialization rate, and doubling rate of rice using anther culture. In our study, we used 3 varieties: Sasanishiki, Hitomebore, and Genkimaru. Sasanishiki and Hitomebore are famous rice varieties developed in Furukawa. Genkimaru is a new variety which is easy to raise. We used 2 kinds of mediums to test the difference of growth between them. By using these conditions, we tested the rate of callus formation, respecialization, and doubling. Sasanishiki comes from Hatsunishiki and Sasashigure. Hitomebore comes from Hatsuboshi and Koshihikari. Genkimaru comes from Hokuriku 188 and Manamusume. We use 2 mediums, N6 and B. N6 is a popular medium. B is said to be a suitable medium for rice. This is the material of N6 medium. Potassium nitrate and ammonium sulfate function as nitrogen fertilizer. This is the material of the B medium. Potassium nitrate and alanine function as nitrogen fertilizer. We will tell you a detailed explanation about our experiment of anther culture. Before cultivation, we had to prepare. First, we placed 8 to 10 seeds of rice to the ragnol pot. The pot contains soil and basic fertilizer. When the length between the first leaf and the second leaf was 4 to 6 centimeters, we placed it into soil. Next, we bathed into 0.5% colchicine solution for a day in the refrigerator to increase the amount of chromosomes. Then, we bathed it in water for 10 days. In the next step, we will tell you how to make a callus. First, we removed the cover of the rice plant, then took out the branch. We pinched the bottom of the young rice and cut it like in this picture. We squeezed the side of the young rice, then it opened. We turned it using the tweezers. Then we could see 6 anthers. We picked them up and put them into the medium to make calluses. We put 18 anthers in one medium container. We cultivated it at 30 degrees Celsius for 12 hours and 20 degrees Celsius for 12 hours, alternately with shading. About 20 days later, we got calluses. We moved the calluses to another medium for respecialization. Then we chose ones under 2 millimeters because grown calluses are hard to respecialize. We cultured it at 25 degrees Celsius at 2,500 to 3,000 lux. The formation rate of callus is the amount of callus divided by the amount of cultivation multiplied by 100. 17 days after transplanting, the callus grew as you can see in the photograph. Respecialization was investigated after 1 month. At this time, well-bred individuals have reached the upper part of the test tubes. A summary of the first stage result. A successful plant. Failure of the plant to grow. Albino mutation formed in the plant, so it's a failure. Only root started to grow, a failure. Only callus was formed, a failure. Contamination from various bacteria, a failure. The successful plant is taken and the respecialization rate was calculated using this formula. The number of successful plants divided by the amount of callus multiplied by 100. The photograph shows that the rice has reached the upper part of the test tube. Tap water was added to it, then exposed to the open air in order to re-acclimatize for 1 week. After this time, the rice was taken out of the test tube, and its roots were flushed with water to clean away the growing medium gerrite. The rice was separated into 6 different batches, and each batch planted into a growing tray with either N6 growing medium or B growing medium. The photograph shows that the rice being transplanted to the growing tray in this experiment on October 31st last year. They were left to grow for 3 months. After this time, the seed pods of each individual plant were gathered. Then, the successful seeds were separated for analysis. The doubling rate could then be calculated using this formula. 2n means the doubling has succeeded and the seeds were produced, divided by the number planted, multiplied by 100. Results of callus formation. By looking at the results of the rate of callus formation on the graph, we could see that all the plants grew better in B medium tray. But it can be seen that Hitomebore struggled to grow well in any of the medium. Sasanishiki and Genkimaru had a high success rate because they were easier to grow form calluses. Results of respecialization. The result of respecialization rate is like this. Please look at this green part of the graph, which shows the rate of successful plants. It can be seen that B medium is suitable for respecialization and every variety. Results of doubling. The results of doubling rate is like you see. The green graph is successful doubling rate from successful plant to 2n. B medium was suitable to double Sasanishiki and Hitomebore. For Genkimaru, both medium had a high rate. Also, Sasanishiki was likely to die using N6 medium. Conclusion. These experiments show that all 3 rice varieties tend to grow better in B medium compared to N6. Second, the doubling rate of Sasanishiki and Hitomebore tend to be more suitable for the B medium than N6. But Genkimaru has a similar rate in N6 and B medium. The reformation, respecialization, and doubling rate of Hitomebore tend to be low, which shows it is difficult to grow Hitomebore. And last, Sasanishiki in N6 tends to die, therefore difficult to grow in N6 medium. Final findings. We wanted to find out the doubling rate, respecialization rate, and the formation rate of callus of the rice varieties and do research on the 2 previous generations of the 3 varieties of rice. By doing anther culture, we could find out about the previous generations' genetic problems so that we can produce better plants for the future. This concludes our presentation. The presentation was brought to you by Michitaka Yamasaki, Daiki Takashima, and Kenji Itabashi. Thank you for listening.
So thank you very much. Professor Yanagisawa, do you have any question or comment?
Thank you very much for very nice presentation and congratulations for your ongoing research, which I guess is very important for, not only for every Japanese, but, for the world. So, you hinted at this in the very last slide, but there is this very well recognized phenomenon called hybrid vigor, or some people call heterosis, which simply means that, for example, the offspring of 2, different strains of, say, dogs or cats or, for us, mice, are stronger than either parents, tend to be stronger. And on the other hand, this anther culture is one way of, almost cloning the individual plant, right?
Yes.
So, by definition, you are essentially reducing the genetic variability of the plant. Essentially, you are making all homozygote plants, which may be weaker than the parent plant. So my question was, in the actual practice of agriculture, for example, rice field, how do they ensure that genetic variability doesn't continue to decrease? In other words, how do they ensure the outbredness of rice strains? That's my question. It's a little bit complicated, but I was genuinely interested.
So the plants can be divided into two types, like autogamous plants, which can pollinated in one plant, or allogamous plant, which is pollinated between one plant and the other one. And so if the inbreeding depression happened in autogamous plants, so they would maybe already be extinct. So we thought there must be another reason, like the or Sasanishiki struggling in N6 or anther culture. So some plants are weak against the stress of the anther culture, so making clones. And I think the reason they were dying was not because the inbreeding depression, but only the stress had happened and maybe they died, I think. So because most plants are autogamous, I think they don't suffer through inbreeding depression, and I think the reason was only the stress. Was it okay?
Thank you for clear answer.
Thank you.
I don't know much about plants, so.
But the keeping the variation is very important. So we can take one more question from this any of our 5 researchers. Do you have any question or comment? If not, then thank you again for the presentation. So the next 3 speakers come from Eleanor Roosevelt High School. Eleanor Roosevelt High School is one of the largest high schools in Maryland, and which is located in the Greenbelt near Washington, D.C. The first speaker is Michael Stevens. The title of his presentation is Fast Adaptive Control Using a Neural Network. So please start.
Hello, my name is Michael Stevens. I'm from Eleanor Roosevelt High School, United States, Maryland, and this is Adaptive Control Using a Neural Network. So this project investigates the use of a neural network as a self-tuning control algorithm. So to start off, give you some background information. Control theory is a branch of mathematics that deals with the behavior of stochastic systems and has many, many applications. It's infinitely useful in robotics. It's used in autonomous steering, in boats, in cruise control in your cars, and even in the air conditioning in your houses. So 2 common terms in control theory are the set point, or the goal state of your system, and the error, which is the distance from your set point. So just to give you a concrete example, for your thermostat, the set point is the value you set on your thermostat, and the error would be the difference between the actual air temperature and your desired temperature. So the most common control algorithm is the PID algorithm, which stands for proportional integral derivative. And the entire algorithm is just a weighted sum of 3 terms: the error, the integral of the error, and the derivative of the error. So this algorithm is actually really simple. It's computationally efficient, it's easy to program, and it's actually applicable to many different types of system architectures. So it's very useful, but it definitely has some drawbacks. Those 3 weights are all functions of the system architecture, which means they're completely different for different systems. There are mathematical tuning methods to find these weights, but they all tend to be very complex and yield poor results. Also, over time, the intrinsic values of your system can change. Let's say friction between wheels decreases, or lighting in your environment changes. You'll have to retune your PID controller. Also, PID control can perform poorly on complex systems. So I'd like to introduce another algorithm to you called a neural network, which is basically a biologically inspired function approximator commonly used in pattern recognition problems. So in a neural network, a single neuron shown here has several inputs and a single output. Each input has a weight associated with it. So when a neuron receives a signal, it computes the weighted sum over all the inputs and passes that value to an activation function, which bounds the output, and the value returned from that activation function is the output of the neuron. In a feed-forward neural network, as shown here, neurons are arranged in layers, with each neuron in one layer being connected to each neuron in the adjoining layer. And neural networks of this type can actually be used to approximate any continuous function with the correct weights, which are usually determined by machine learning techniques. So if you look at a PID controller and a neural network mathematically, you can actually view a PID controller as a degenerate case of a neural network, which it's a neural network with 3 nodes in the input layer, no hidden layers at all, and 1 node in the output layer, with the 3 weights being representing the 3 connections between the input layer to the output layer. So this gives us a very intuitive way to expand PID-like control to more complex systems using more complex network topologies. It also gives us an intuitive way to construct a self-tuning algorithm using machine learning techniques. So the actual experiment in this project is a simulation in which a robot attempted to follow different path functions. Different neural network controllers were tested along with a standard PID controller for comparison. And to make it a little more realistic, I added stochastic movement with a Gaussian noise. So here's a sample from the results of the experiment. As you can see, both controllers successfully operated as feedback controllers. And the PID controller as shown here was hand-tuned, and the neural network controller was allowed to learn until convergence. It started with an average error of around 30 and converged to an average error of around 8.4, showing that neural networks can indeed operate as self-tuning feedback controllers. However, it didn't perform as well as the PID controller, and I believe there are 2 main reasons for that. One is how each neural network controller was at least twice as complex as the PID controller, while this simulation was actually quite simple and didn't need such a complex controller. Also, the learning algorithm used in this experiment was error backpropagation, which is notorious for falling into local minimum solutions or suboptimal solutions. One way to get around that is to instead use a learning algorithm from the field of reinforcement learning, which takes into account something called exploitation versus exploration, where the learning agent has to decide whether to exploit knowledge it already knows about the environment or to explore possible new actions to get more information. And this can help avoid falling into local minimums. So I believe the future of control theory is strongly tied to machine learning techniques, such as CLCLA or policy gradient methods. Thank you.
Well, thank you very much. Any question or comment from you, from 5 of the researchers? Maybe Professor Yanagi-Sara can ask some question, application of a neural network to your study of sleeping, maybe consciousness or something like that. That would be very much connected to the neural network.
Yeah, please join my team to model the sleep and wakefulness.
Here, actually, in Japan, those kind of research is a little bit shortage, and so you are very welcome to come to Japan to help us to study. Yeah. Okay, so let's move to the second speaker. The speaker is Matthew Ari. The title of his presentation is Cooling of a Linear Induction Launcher. So please start.
My project was centered on the use of cooling to change the velocity of a linear induction launcher. Basically, the best way to explain what a linear induction launcher is it's basically a magnet that has a current run through it for a very short period of time to create an electromagnet, which pulls an object, a ferrous object, forward, at which point it stops being an electromagnet because it only acts as one for a very short period of time, and the object just keeps on going. So my hypothesis was that cooling the linear induction launcher would increase the velocity of the projectile. And basically, my idea was that I've heard about experiments where cooling the circuitry would allow the electronics to function better. And I was just trying to figure out how exactly it managed to do that, and what exactly the effects were. This is my breadboard. As you can see here, the current flows in with around 5 volts, and it goes into this circuitry. Over here you have a timer switch which controls this transistor to turn the current on and off. So it's a pulsed charge, and it's basically alternating current. And once you have an alternating current, it can go through this transformer to bump up the voltage from 5 volts to 500 volts. Once it's at 500 volts, it goes into here, which is a rectifier, which the voltage is recorded. And once it's in this rectifier and it's converted to direct current, it goes into this capacitor bank, which charges up to between 200 and 240 volts. Once it's at the desired voltage, which I kept at an average of 240 for my experiments, this button is pressed, which causes 2,000 volts to go into this plasma switch. The plasma switch functions by, once you have plasma, it's able to complete the circuit, allowing for the electricity to flow through this coil, creating an electromagnet which fires a projectile. Here's my schematic. As you can see, there's the 5 volts and my timer circuit and everything else. Over here is where the launcher is. Basically, for my tests, I created a small chamber using a yogurt container in which the induction launcher was placed, so that I could control the temperature by adding different substances to the environment. The difference, yeah. Anyway, basically, to record my results from room temperature, ice, and dry ice, I recorded the sound of it firing. Here's where it was fired out of the tube, and here's where it's hitting its target. I recorded it on my iPod. Anyway, once I had the sounds, I just put them into Audacity, and I got the time. These are my results, which are actually quite interesting. Over here, you have the velocity plotted against the temperature. So as you can see, at room temperature, the velocity is quite low. And as it gets colder, the velocity goes up. There's an inverse correlation between the velocity and the temperature. Over here, this green line is the linear regression, which is basically the average velocity, and it's showing how it would continue up until the point that reached zero resistance, at which point it would no longer apply because it would flatline. Over here, you've got the velocity of projectiles plotted against the coil resistance and the temperature. As you can see, the velocity as the velocity increases and the temperature decreases, the coil resistance is also decreasing. So basically, the reason it's going faster is because when the atoms are colder, they're closer together because there's less movement and less jittering, because atoms are constantly in movement, and when they're moving less, they're able to transmit their electrons easier because they're closer together. And basically, that's my results. So my conclusion was that the projectile speed was inversely proportional to coil temperature, which means colder is faster. And I would like to thank the Advanced Institute for Material Research at Tohoku University for sponsoring my trip to Japan. I really appreciate that. Thank you very much.
Thank you very much. So, question, comment? Maybe Dr. Takayama, could you make some advice to the team?
So congratulations on your research, and maybe you used the liquid nitrogen, so very low temperature, so minus 100 degrees. But how do you?
How did I know that it was that temperature?
Yeah.
I actually had an electronic thermometer outside of my my closed system, so that I could monitor it without affecting the temperature. And basically, I made sure that it was at a uniform temperature. And if it deviated from that uniform temperature, I did not use that in my test results, and I added or subtracted ice or dry ice to get it back to a uniform temperature.
Okay, I see. And so that's result is good, but very, very low temperature. So how we can application for
the real world?
Yeah.
Oh, for instance, you could run trains underground rather than running them on the surface to keep the temperature lower, because when there's a lower temperature, there's more efficiency in an electric engine, and for the magnetic levitation, you could run the same system with less energy, and it would be more efficient.
Okay, thank you.
Thank you very much. So the last speaker is Vishnu Rachakonda, and his title of his presentation is Fast Single Point Imaging, Electron Paramagnetic Resonance Imaging to study fluctuation tumor physiology. So please start.
Okay. Konnichiwa, everybody. So my name is Vishnu Rajakonda from Eleanor Roosevelt High School, and the topic of my presentation is fast electron paramagnetic resonance imaging to study fluctuating tumor physiology. As we all know, cancer and metabolic indicators of treatment progress are very active areas of research. We all know cancer is very important, but beyond that, understanding any disease or cancer at its very root, at its very metabolic causes, is very important for treatment progress, to understand that. And one such instance is tumor hypoxia. When tumors have less oxygen, it is directly correlated to a much more aggressive phenotype, where the tumor is much harder to treat, and it results in drastically worse results. So it is highly desirable for us to be able to understand the dynamically changing aspects in tumor physiology, specifically metabolic indicators. We want to understand what goes on at the very basic chemical level of every tumor, especially with respect to hypoxia. So electron paramagnetic resonance imaging, EPRI, is an emerging imaging modality in the biomedical sciences. You may have heard Ms. Takayama talk a lot about imaging electrons, and this is exactly what we are doing with EPR. We are imaging the spin. So EPR can be used to image the spin dynamics of molecular oxygen, the critical free radical and part of tumor hypoxia that we need to understand in order to plan treatment progress using metabolic indicators. EPR is a relative of MRI in that MRI images protons using magnetic resonance. EPR images electrons using magnetic resonance. And the goal of this research is to reduce EPRI scan times, because currently, since we're imaging electrons, which are much, much smaller than protons, the time that we must use, or the time that are the in vivo clearance times when we are imaging a human body using a tracer, are much smaller. And currently, EPRI cannot produce good enough images for us to be used in the clinic. And we need to reduce the time taken to produce these images. So what are the methods? K-space, which is just the raw data collected by EPR, the acquisition of this must be optimized. So two features of K-space are taken advantage of. One is conjugate Hermitian symmetry. As you can see, this is a map of conjugate symmetry, whereby 50% of the data is matched across the axes. So essentially, you can use 50% of data instead of taking 100% and just use the Hermitian function to simulate the other half, and a limited region of high energy density. As you can see, there's a tremendous spike in the middle. Essentially, every single point takes the same amount of time to image, but not every point is equally important. And we need to take advantage of these two features of K-space. So the methods that we used, number one, partial Fourier techniques. We implemented certain algorithms which had previously been studied in MRI, but in novel cross-application to MRI because we're using EPRI, because we're using a new type of EPR called single-point imaging EPR. We use multiple algorithms. Partial acquisition reconstruction through the elliptical reconstruction acquisition, and then we merge partial acquisition and partial Fourier, specifically elliptical and conjugate synthesis and elliptical and homodyne. That's a map of how we merge them. And then, in order to improve the temporal resolution, just as Ms. Takayama was saying, to improve temporal resolution, we want to not just image picture 1 and picture 2, but picture 1, 2, 3, 4, 5, 6. So we implement a trajectory, innovative new trajectory, which uses a Cartesian spiral to image the dynamically changing area in the center first. And then the dynamic acquisition, which uses one scouting image, and then multiple partial scans of only the important area, only the most dynamically changing area, right here. And this optimizes acquisition and improves temporal resolution. So experimentation, partial Fourier and partial acquisition methods were tested in MATLAB using computer modeling and phantom in vivo data, phantom data, in vivo data. And experimentation, I designed these experiments. The coil tube test for trajectory designed. Essentially, we have one oxygen mimetic tracer here, spin tracer, OXO63, and it was dynamically moving through the coil, similarly for the W tube. And as this dynamism happened, we implemented these methods to test and see if the actual dynamism would be represented more effectively using these new methods and result in better temporal resolution and data acquisition times. And so the results were that all methods showed significant results. Partial Fourier and partial acquisition methods demonstrated significant time savings. At 64% of K-space, conjugate synthesis, a PF method, had an RMS error of only 4%. That means with an RMS error of only 4%, we saved 36% of time and clinical quality images. Furthermore, the trajectory design experiment, which uses the spiral trajectory, was justified conceptually but is dependent upon the K-space model, specifically the shape of it. And the dynamic acquisition was a stunning success, as the W-tube phantom posted results, clinical quality results, in 12 minutes as opposed to 50 minutes for traditional K imaging. And in vivo data showed that only 20% of data was needed to produce clinical quality images. And so as you can see, the conclusion, the methods shown have demonstrate significant time savings, and further research can be done to merge the methods shown. Thank you.
Thank you very much. Question, comment?
So, what was the most difficult part in your research?
Understanding the background, because I had to get used to reading very complex, very dense articles, and I had to understand both biology of tumor hypoxia and the spin physics and whatnot of MRI and EPR, which I had not been particularly familiar with. So that was the most difficult part.
Yeah, fantastic.
So currently, what's the actual most significant obstacle of applying EPRI for actual clinical settings?
Yeah, there are a number of factors. One is obviously this fact that we can't produce clinical quality images easily. Second is the fact that there are a lot of different aspects that would need to go through for the US FDA testing and whatnot. For example, the tracers that we use, they're not currently approved for human use. Additionally, the equipment used is very expensive. We had to order these equipment from defense contractors. They're not released to the general public. So there are a lot of facets that need to be addressed, both biologically and engineering-wise. But it's possible that in the next 20 to 30 years, this could see clinical use emerging.
Is there any other question or comment? If not, let's thank all the three speakers again.
Thank you.
So the presentation schedule are all over. And so all the presentators, could you move forward and come up to the stage? And also, unfortunately, Professor Itami has to go back to catch up his flight, and so he will just go back to home and so on. So thank you very much, Professor Itami. So I would like to hear a few words from Professor Greer on all the presentation.
I would simply say I think all the presentations were wonderful, beautifully clear, well prepared, and with excellent science behind them. So very, very impressive. Thank you.
So Professor Hirose.
Yeah, I'm also very much impressed with the fact that your presentation is very, very well prepared, and it must be a very good experience for you for the future. And I'm, even jealous. Thank you.
So, Professor Yanagi-san.
Yeah, I also thought that I wish to have this type of experience, when I was high school student. So I really envy you. And also, we all learned today that, style of experimentation, style of presentation differ, from each other very much, right? So don't be worried about being different from others. That's my message.
Please, Dr. Takayama.
Thank you very much for wonderful and interesting results. So each research has a good viewpoint. So I got 異常感知能力 and so Japanese high school student. So you are great. So because I weak in English, so I admire your ability.
Oh, thank you. So finally, we would like to give a certification of giving a presentation on this WPI Joint Symposium. We don't have enough time to give a certification to all students, unfortunately. So we would like to give the representative of each school. So Professor Greer, please. So next, Professor Hirose. Professor Hirose. So Professor Yanagisawa, please.
Congratulations.
So Professor Dr. Takayama, please. Yeah, so that's all the schedule we planned. So let's thank all the speakers again. 本日は1時から大変長い時間たくさんの講演にお付き合いいただきましてどうもありがとうございました。講演者の皆さん研究に対する大変な熱情と愛情を持って研究されている姿が伝わったかなと思います。また研究というのは非常に多様で興味富んでいるということも分かっていただければ我々の意図するところでございます。今日は本当に長い間お付き合いいただきました。高校生の皆さんも素晴らしいプレゼンテーションで私自身大変感動いたしました。今日はお運びいただきましてどうもありがとうございました。WPI の研究拠点、今9つございますが、みんな社会、人類のために新しい研究成果を出そうと思って頑張っているところでございます。皆さんのご支援とご協力よろしくお願いいたします。じゃあ今日どうもありがとうございました。先ほどもアナウンスいたしましたように18時までブースセッションを行っております。先ほど全部ご覧にならなかった方はお帰りの際にお立ち寄りください。じゃあ今日どうもありがとうございました。
皆様、本日はサイエンストークライブ2013 by WPI 第3回世界トップレベル研究拠点合同シンポジウム in 仙台にご参加いただき誠にありがとうございました。皆様の率直なご感想をお聞かせいただきたくアンケートのご協力をお願いいたします。お帰りの際、出口付近のアンケート回収箱へお入れください。